Hi, and welcome to Photons from Space. In this video, is part 3 of editing astrophotography photo. It's a photo of the North American Nebula. It's shaped kind of like North America. We're going to start with review of the pre-process. Well, first of all, the first video was we went through and selected the raw frames that we wanted to pre-process. We looked at any images that might have defects and rejected those, and we included those in this. And then the ones that were good, that didn't have airplanes flying through the image or satellites that were too big for the pre-process routine to take out. We deleted those images from the sequence. And the second video, we actually did the pre-calibration and stacking of the images. In this video, I want to start by reviewing the calibration and stack, what the image looks like going through that process, and then we'll go right into the post-processing, where we get rid of some of the noise. We normalize the image. There's actually, looking at the list, there's three steps to this process. We normalize the image. Namely, we take the background, try to flatten that out, because sometimes you have light streaking across the image for whatever reason, and that has to be equalized in the background. The software I use will actually do that. We take out some of the extraneous noises that are there that we can kind of filter with some of the math that the software can do. And then the last part, we actually stretch the image. We take the histogram where the largest majority of the pixels are toward the black end of the image, and we spread those out across the histogram to bring out the image itself, bring it to life. And so we're going to do that in this video. So hang on to your bootstraps. Here we go. Okay, so here we have three images. The first one is a single frame of the raw image. The nebula, the North American Nebula, is upside down in these three. Once we get to the post-processing, we will be working with a flipped image, flipped in the about the x-axis, in other words, top to bottom. So, looking at this upside down, you have what looks like Canada down here, and you have Mexico trailing up here, and Florida over here. So it's one thing you probably don't really notice off the bat is the edges around the image are darker than this in the middle. This next image, going to this, there's just a subtle difference. Go back and forth a few times, and you can kind of see where the middle, in this image, the middle is brighter than this. And when we go to this one, it's kind of the same brightness across, but we still have the details. And so that's what the difference between these two images is. The second one is calibrated. We have this what's called vignetting. Sometimes we have dust bunnies. We don't see any in this image, but we do have vignetting. And so by doing a calibration, we calibrate that out. We take what's called a flat frame. It's just a white light shined through the telescope, and then that vignetting will happen in that flat frame. And so in the software, when it goes through each frame, it actually looks at the flat frame and looks at the light, what's called the light frame that it's interested in. This here is a light frame that's compared against the flat frame, and the result is this calibrated frame. And then to really bring things out, we stack all the images, all this noise, it's random noise gets reduced. And this situation is a factor of 10. The reason I know it's a factor of 10 is because we have 100 images. And in doing the math, the amount of signal to noise ratio improvement is square root of the number of images that you stack. And since we're stacking 100 images, we're reducing noise by a factor of 10 and keeping the signal. So going to this, you see a huge improvement in the image. There's no it's the difference is blatantly obvious. And so now let's go from this to actually, we're going to go and actually do the post-processing. This is the inspection. We've pre-processed and now we're post-processing. And we start with the stacked image. This sets the directory. Now we start with a stacked image. And as I stated earlier, this gets oriented correctly, where the up is north and down is toward the South Pole. And we're auto stretched. This is what the image looks like. It's kind of boring, but to do the early stages of post-processing, we have to be able to see the image without affecting it. And that's what this auto stretch, that's just auto stretching the output display. It's not really affecting the image itself. So the first thing we want to do when we post-process, when we stack images, the telescope moves around slightly every 5 images to help smooth out the background for stacking. And in doing so, you get what's called artifacts around the edges. It's not real obvious in this image, but here you can kind of see that this area here is a little different from this area. So I usually draw a box there and start with that, and start stretching the box, and kind of go in with what I think is, and just get rid of those areas around the image. The reason we're doing this is when we do post-processing, if we have these artifacts and we're doing a mathematical function on these pixels, these artifacts will actually affect and distort the final image. So we want to remove these artifacts that are going to cause problems in that final image. If I wanted to, this star here, it has an odd shape. I'm not sure. This has been kind of bothersome, but I'm going to leave it. But if I really wanted, if I was going to be too bothered by it, I would actually crop that out. But the main thing is to get rid of the problem pixels. And I kind of want to square that up a little bit. And we will right click and crop. Okay, next thing is we want to desaturate the stars. So we come down to star processing and click desaturate stars. It took about 1.5 seconds to do that. And we can look at any effects that it had by undo and redo. You don't see where it really did much of anything. This one is obviously, this star is probably blown out. So we might see some subtle changes with it. Not a whole lot. Maybe go to a linear and see it's there in the linear. Oh yeah, there we go. That's That's what I wanted to see. So going back, we see this thing's blown out. This white area is literally flat. If you looked at the histogram on this, let's see if we can actually do that. It's probably up here somewhere. It's too bad we can't really. Next one is that. So yeah, I don't really see how to measure that, but obviously this is blown out. And when we do this desaturate clip stars, it makes that more of a rounded. If you can imagine the brightness of this being graphed vertically, going across, it's more smoothed out. So that's what we're doing when we do this desaturate. This one, same kind of thing. So it's just taking and normalizing the image. So we'll go back to the stretched. So in the auto stretch, I guess that difference doesn't really show up, but obviously it was needed. Okay, now we're going to do a background extraction. It doesn't really look like it's going to help much, but we're going to give it a try because I think it might. And so what this does, it adds point. It puts points in here where it thinks there's where it thinks the background is, and then mathematically will flatten that. It'll make these dark areas evenly dark. So we're going to generate this. Yeah, that's not good. I don't think that. So what's going on here? We'll revert back. There's our problem. Too high. So we're lower that sensitivity down. Get rid of some of these where we know we have nebula. And where I have some at the edge, I'm going to move them out away from that. Okay. And we'll do a compute background. And we'll go ahead and apply that and take a look and see if we like the results. That's without and that's with. Yes, I think it brought this out. But I'm not sure if that's really a good image. I tend to like the original better. Yeah, I think I'm going to trust the original and not do background extraction on this. This is rather complicated. Where you have a nebula that takes up the whole frame, it's really difficult to do a background extraction. If this was a galaxy that was in the middle and I had uneven background, then this background extraction would even that out and make it better. But having this where the nebula is going off the edge of the screen, it's not going to give really good results to do an extraction like that. And now we do what's referred to as a color calibration. This is going to be photometric. And so what we're going to do we are going to look up the North American Nebula, get the actual number in GC 7000, because C20, the catalog in this software doesn't seem to know what C20 is, but it does know in GC 7000. We find that, and there it is. We also want to do dynamic PSF. This is where it picks out the stars in the image. They have to be 0.3 to 0.7. And we have enough stars there selected. And so let's go take a look and see. Okay, it's picking out these stars. The bright stars it's not picking out. These are kind of in the middle of the brightness of the image. And so what this is going to do is use these stars and do what's called a plate solve. And it's going to determine where this telescope was pointed and look through its catalog of what the color should look like, and adjust the color brightness to balance and get the proper color of that image with what's in a database up in the cloud somewhere. So I'm going to hit OK. Close it out. Let's look at our what was done. Found solution. Okay, so it's catalog. 35 stars used for the calibration. A solution for the colors. This is what it adjusted the color. Make plate solving, so found no bad size. So it did a plate solve and actually adjusted the color. And so what we want to do now, come back over here and actually turn those circles off by getting rid of all the star selections. Now what we want to do is go look and see what the color did. We have some red in here. Going back before, it looked like there was kind of a greenish tint to the red. And when we did it, it kind of turned that down a little bit. So it didn't really change our color much, and that's kind of a good thing. That means we were pretty close already by default. So yeah, so I'm definitely going to keep that change. Now we're going to remove next is this image. You really can't see it. If you zoom in, you see some green pixels in through here. The way this color images are taken when they're taken in the telescope, the camera has four different color pixels per one, what would be called a luminance pixel, but basically the total pixel brightness is represented color-wise by 4 pixels. A red pixel, a blue pixel, and 2 green pixels. And by having 2 green pixels, the green tends to be the stronger color in the image. And so what this next step does is basically balance out, remove green noise. So we click on that. We're going to there's a protection method to protect the color integrity. It's doing what's called an average neutral. What that's doing is taking the background and averaging it out to a neutral color. And it's going to, so when I hit this apply, it's going to take out those greens or reduce them. Hit apply, and so you can kind of see where that was reduced. Go backwards and forwards. And so, yeah, that definitely did the trick. Zoom out and look at the difference again. Yeah, there's a slight green tint. Go forward. It's more of kind of the white tends to be more bluish, giving me it's more of a white instead of a green tinted white. And now we're going to do some more noise removal. Some of this noise we see is what's referred to as salt and pepper noise. Should be noise reduction. Yeah, where'd it go? There it is. Okay, noise reduction. And we click on this remove salt and pepper noise. And we're going to do this VST function images where noise characteristics are not Gaussian but primarily Poisson or Poisson-Gaussian mix. So most astronomical images, when you take them in a CCD camera or a electronic imager, like we did here, the noise is primarily Poisson noise. And so this is going to reduce that. And we're going to cut this what's the modulation? Pixel is calculated 1 minus m, 0.5, so it's 0.5, b plus 0.5. So it's not going to do a total on this. We'll just apply the half. It takes a while. It took about 7.25 seconds on that. Let's see what that looks like close up. Yeah, it kind of smeared that a little bit. I can see a little bit of, you can see the individual pixels, and when you go forward, it kind of blurs the pixelization out. So it kind of mixes those pixels together, and it gets rid of some of that. Zooming out, yeah, it adds just a tint of clarity to it. So I like that. Just for grins, I'll look and see what the noise does. If I turn the modulation all the way up to max, click apply. Wow, that really blurred that. Yeah, it's kind of too much. I can see now why they suggest only using 0.5 on this. I'm going to go 0.6, take it back, and hit apply again. And see what that does. Yeah, blurred it. It left some of the pixelization in there. I'll go back to what's recommended. Hit apply. That should be fine. Yeah. Okay. So we'll go with that. Okay, so that completes the denoising. We'll save this image to the whoops, that's the stacked. Not what I wanted to do. So I actually want to save that to the normalized. Replace it, save. Okay, so this is what we have in the normalized image. Unfortunately, we destroyed the stacked image, but we can get it back. Go back to post-processing. Pre-process, get this one. Copy. Copy that. Delete the stacked. And rename that. That's my original stacked. Okay, now we have the normalized image here. The stacked image we started here but came down to here. And now we're going to do the deconvolved image next. And to do that, first we will take this and save as deconvolved, because we're going to deconvolve this. We've done it before for the video, but I'm doing it again for the video. So I'm going to save. And I want to replace it. Save it, and now we're going to open that deconvolved. So this is the normalized image that we're going to deconvolve and save it back into the deconvolved file name. And deconvolve is pretty quick. It's we first go back and select our stars that we want to look at. Okay, we have those. Those are circled. And so what the deconvolution is going to do, it's going to take this star. You can tell by this is not a perfect circle. It's a little bit egg-shaped, just ever so slightly. And it's going to that's a distortion, somewhat with the atmosphere, with the movement of the telescope, you name it. So what the software does is it knows what a star should look like. So this distortion gets represented as a mathematical function. And then the software takes the inverse of that function, applies it to the whole image, and these stars get turned into perfect stars. And the rest of the image hopefully will be reverted to a more representative, more accurate representation of what's in the sky. Sounds complicated, but it involves what's called a two-dimensional Fourier transform. In college, I had to study this. Got to actually use it back in the 90s on a photo, and it was to recover a blurred image. I won't go into much detail here. I want to stay on the astronomy. But so we're gonna Fire off the deconvolution window. First thing we have to do is we have to get our star from, we're going to take all these stars that were selected and average them and get an average representation by generating that. That's the an average of those stars. It's not, you really can't tell, but it's not perfect, but it's really close to a perfect star. And then we're going to apply the deconvolution. This is the method. There's different methods. We're going to stay with the default. Just a Wiener filter. I don't think that's proper. Richardson-Lucy method is what's normally used with astronomy. I'm not sure what all these, total variation. Yeah. Anyway, we'll leave that default. And then we're going to go through, this is there were just the gradient descent step size and the iterations, the number of times this is applied. So it applies a little bit 10 times. We'll hit apply and we're going to zoom in and just see what that does to these stars. If it makes a dark ring around it, we will back that off. And it does take a while. It says Siril FFT wisdom imported successfully. That FFT is a Fourier transform, which it convolution and deconvolution. Convolution is a image. In signal analysis, it's a time function, very complicated. To simplify that function, you do a Fourier transform. Then you can do simple multiply divide to convolute and deconvolute. This is doing a divide, and we overdid it. These dark rings are overdoing. So we will start bringing this down to 0.2. Revert this back and apply it again. It seems to go faster once you got this done once. Yeah, the ring's still there. 0.1. Go back and apply it again. That's better. There's a hint of dark rings around some of the dimmer stars. Back to an 8. And we'll hit apply again. Okay, there's just a hint of darkness. I'm going to leave it at that. One thing I want to do, I'll close this out. Look at the linear image and just see how that looks unstretched. And it doesn't really change it much. Not much at all. Still more in the stretched image. Yeah, I'm going to zoom out to the maximum, go backwards and forwards. Yeah, I can see a hint of change. So for the sake of accuracy, we will leave it at that. And And part of this, one thing I've learned to do a little bit is go back and do another median filter. That tends to kind of blur that back out a little bit, and the deconvolution takes it from a from a distorted blur, sharpen it, but it brings noise back, and this median filter blurs it back, but without the distortion. It does it in a linear fashion. So some of these artifacts that you get from convolution, some of this peppery noise that results, we didn't add too much, but if I zoom in here, you can kind of see where going convoluted, it tends to highlight some of these pixel differences, and then filtering it blurs it back out. And we will look at the salt and pepper noise again, noise reduction. See if that's really going to help us any. Yeah, I just hate to go back to that. I think I'm going to leave that on. I think I will leave that in there. Okay. And so that's the end of our deconvolution. Next thing we're going to do is stretch the image. So let's go back. Turn the star circles off. This is saved to the deconvoluted, and we're going to save a copy to the stretched. That's what we did last time before the video. Replace and save 32 bits. And we take this back to a linear. So we're going to open up deconvolved. Now we're going to work with a linear image. And we're going to stretch the histogram. So this is where it gets fun. Generalized hyperbolic stretch. And the first thing we want to do is this localized stretch. We want to take it to maximum. We want to zoom in on the dark pixel peak, the peak of the histogram. And we're going to click into the peak and the symmetry point. It places the transform turns into an S curve, and it's going to be mostly under this peak here. Mostly getting stars here. I'm going to take this back and actually do Cancel out of that. Stick to the original plan. What others are doing. .46 and take this to maximum. Back to a 1, zooming out, and we're going to see how this is our transfer function to move these pixels from the dark over to the light. And we will start seeing our image come out. And that's generally where I stop it. Set that to 5. We'll get just a hint. This is a straight line here. I want to move this to the left. That's where these linear protection, HP and LP. The LP is a linear protection, protects the low. It makes this dark side linear. And I did that wrong. Yep, messed up. Click under here to get the set point 44. We can linear protect that on the low up to 44, and the high protection is what I was going to show. This all the way to the right, that back to 1. Bring it to a 5, and we start to see our nebula appear. This is a straight line here. We can bring this down to protect that and actually make that a linear curve. Take this up to, say, a 6. Okay. Now, and when we hit apply, that captures that profile and gives it, and then we can start going over finer details. I can actually bring out some of the details. Pull the contrast. image. Or get some contrast in this image. I'm actually making where there's definitive light and dark in here. Some of this could be done in GIMP. I'm liking that. Okay, so now we're going to go ahead and save this as a stretched image. Let's reload this deconvolved. Yeah, should have saved. Should have loaded this deconvolved. I think I still had the histogram of deconvolved. Okay, let's save this as a stretched. Replace, save, open, stretched. Now, let's go back and do the stretch again. Good repeat review. Learn through repetition. Click in here, around the middle somewhere. I tend to go just to the right of the middle. If you like to go to the left, I like bringing the background out too much. And this B, we're going to do the whole stretch. And this comes up around 5-ish. Okay, one thing we notice here when we go to stretch this again, it bunches up the image, part of the image that's close to the brightest, which would be these stars. It tends to really distort that. I don't like that. So that's where this highlight protection point comes into play. We bring that linear, bring this down, making that a straight line. You can do the same on the negative side, but we're not really interested in that. And it only goes wherever your symmetry point is. So if I'd have to bring the symmetry point up. And if you notice, I wrote it up and it bumped this guy back up. So I'll bring him back down. Bring it back down to here. So you can actually linearize this back in, which I don't. I like keeping this as close to black as possible. And we are going to stretch this guy and keep our stars linear. Okay. Apply that. And that's a pretty good image there. Another technique, which I'm not going to cover here, is to actually remove the stars and do just the nebula. It's rather complex. I tend to like having the stars be more whatever I brighten the background, bring the background stars with it. You can actually see what's in the image. It's a matter of taste. And so we're going to close that out. Save this under the stretched. And we're going to call that done as far as Siril is concerned. One thing I do want to do is save this to the GIMP. Copy, and I also want to save it. I did a fit file for GIMP. I want to do a TIFF. And up here where it says Astro TIFF, I want to change this to standard TIFF. Close this. Bring up the almighty GIMP. And we'll do some stretching in GIMP. Do some final tweaks. TIFF. Open. And I go ahead and convert. First thing I want to do is save as. This is going to be XCF, which is GIMP's native file type. And I want to go into the GIMP directory and save it in there. replace. Okay. Now I kind of want to make this flatter, so we're going to fill this in here. But I also want to take out this little sliver here. So we're going to go colors, levels. So that darkened that side a little bit. We could take that out, but I don't want to take everything to the brightest point at this point. File, save, colors, curves. This is where it gets interesting. See, most of the nebulas in this area. And I can actually click on the screen, and this vertical bar tells me where I'm at on the histogram. I get over here on the star, it goes way over there. So I want to take this area and move it over and keep my midpoint about, just looking at the way this is. Probably want to point right there. Point right there. Okay, so now what I want to do is split those two. Yep, so now when you look at the image, you can kind of see where there's some contrast coming out. Okay. Okay. Okay, so there we got that. I'm kind of happy with that. It's different. It brings out some of that red. Just miss the histogram. There's a little blip in there, kind of distorted, but I like it. It makes it interesting, makes it unique. It's something that that's where the artistic part of this comes into play. Uh, Astrophotography is much art as it is science. I enjoy the scientific part of doing this image processing, capturing the images, knowing where to look, knowing where things are in the sky, and just kind of watching things through the season, dealing with the weather, the clouds, visibility, humidity. There's a lot that you have to pay attention to when you're going out to gather light. Gathering photons it's a fun hobby. I enjoy it. So if you enjoy it, enjoy the journey with me, and just don't forget to look up. And while we're here, let me come back on. And so I hope you enjoy this video. If you do, like and subscribe, and watch for further videos. I like to show my screen when I'm gathering photons from space, and just enjoy the being out in the weather, out in nature. I sometimes when I'm out there, we have armadillos come through, dealing with mosquitoes, bugs, you name it. It's a challenge in different respects, and it's just a great experience. So enjoy. Again, like and subscribe. Bye for now.